We are looking at Chapter 6, which is our introduction to the normal model and using standard deviation as a ruler. The first thing we talk about is data shifting. How does the summary statistics, how do they change when we change the data? For example, what happens if we added 10 points to everybody's quiz score? What if we multiplied the quiz score by 3 to make it out of 30 instead of 10? How does that change our statistics, which is the mean, the median, the Q1, the Q3, the min, the max, standard deviation, interquartile range, and the range? Well, we have two types of statistics. The first one is the measures of position. Measures of position are the mean, the median, the Q1, the Q3, the min, and the max. We don't really have to do, we're not subtracting anything to get them. They're not measuring spread. So measures of spread are the standard deviation, the IQR, and the range. If we have points, let's say our data kind of looks like this. And I have a number line. Let's just say it goes from 0 to 10, and let's just make the median 5, okay? If I add 5 points to everybody's score, or if I add 10 points to everybody's score, the minimum becomes 10, the maximum becomes 20, and everything else just adds 10 as well. Okay, so if we add 10 to all the data points, everything else moves up 10. And notice that my range between here and here is still 10. My interquartile range is still, let's just say it's 5. Let's make that 2.5 to 7.5. We're just simplifying our calculations. Our interquartile range, our range don't change, and then in turn, neither really does the standard deviation. But if I do the rescaling, that's multiplied by a number. So when we translate, that's adding a constant. We've translated graphs in Algebra 2. The rescaling is like shrinks and stretches, to be honest, but we affect the measures of spread differently when we rescale. So the translations did not affect the measures of spread. But if I were to multiply the minimum by 2, all of the values by 2, now my minimum is still 0, but my maximum is 20. My median is 10, and my Q1 is 5. And you can see if I multiply everything, all my points, if I multiply all of the data points by 2, I've now increased my range by 2. And I've increased my IQR by 2, right? It went from 5 to 10 now. And so the measures of spread are affected by multiplying or dividing. Like if I were to divide them all by 2, all my data points by 2, this is how it affects the summary statistics. So my measures of spread rescale but do not translate. They do not translate, but they rescale, meaning I can multiply them. And my measures of position both translate and rescale. This is important because we don't want to have to go through a list of 100 data points and add and multiply them all by something so that we can find the new summary statistics. We should be able to use this idea just to add to the mean, median, and multiply the standard deviations. Now here's an example of how we're going to apply that. Suppose we took a quiz and it was a 40-point quiz. The results show that the mean is 30, the median is 32, the IQR is 8, the standard deviation is 6, the minimum is 12, the Q1 is 27, and your score is a 35. If we look at your score here, the difference between the Q1 and your score is 8, which is the IQR, which means you are actually Q3. And that's important to note because I want to show you that as we're changing things, that the IQR, the difference between there is when it does change and when it doesn't change. So if I'm going to weight the quiz as 50 points and add 10 points to every score, then your new score is now a 45. But how does everything else change? Well, remember that measures of spread don't change. So the IQR and the standard deviation are going to stay the same. They stay as 8 and 6. But all the other measures of position, mean, median, Q1, minimum, Q3, will add 10. So my new mean is 40. My new median is 42. My new minimum is 22. And the new Q1 is 37. Notice here, the difference between my Q1 and my Q3 is still 8. So my IQR didn't change. But what if I decide to weight the quiz as 80 points? And I'm going to multiply all the scores by 2. So I'm going to double your original score. So we're coming back to this original statistics. And I have 70. That will be your score. So we're doubling the original, so that the original score. So what happens is the mean doubles. So I get 60. My median doubles. 32 times 2 is 64. My IQR is supposed to double. We'll verify that later. And same with my standard deviation. So 6 times 2 is 12. My minimum, 12 times 2 is 24. And 27 times 2 is 54. And now again, look at the difference between Q1 and U, which is Q3. Now that difference is 16. So you can see that the IQR did get larger. And then the last one is, what if we decide to do both things? What if we decide to multiply it by 2, but then also add 20 points to make it out of 100? So the new score, total points is 100. Your new score is 20 points plus this column here, because we already multiplied it by 2 here. And so that becomes a 90. So my new mean is an 80. Multiplied it by 2, added 20. My new median is 84. My IQR is still 16 because I multiplied it by 2, but it's not going to be affected by adding the 20 points. My standard deviation is also going to stay just multiplied by 2. We're not going to add to it. The minimum is going to add 20 points, so that'll be 44. The Q1 will add 20 points, that's 74. And you can see the difference between Q1 and Q3 is still 16. So even though I moved them all, I didn't change the IQR. The distance between those measures stayed consistent when I'm just translating them. When I'm rescaling, then that distance, that range gets larger. One of the things we do in this chapter is called standardizing. We standardize a score by using what's called the z-score. The z-score tells us how unusual a value is by measuring the number of standard deviations a value is from the mean. If a z-score is positive, it tells us that the value is above the mean, and a z-score that is negative tells us the value is below the mean. The z-score is not affected by changing in units, which is one of the reasons why we use it, because whether I'm comparing feet or yards, the number of standard deviations from the mean I am doesn't change. The calculation is z is equal to x, your sample, minus the mean divided by the standard deviation. Sample minus mean over standard deviation. This is a pivotal, super important equation. We use it all year long, and so being familiar with it is helpful. What standardizing does is it allows us to compare things. Which one is more impressive when I'm comparing more than one measurement? For example, in a decathlon, how do I know what's better? Winning the race by a certain number of seconds, or jumping farther in the long jump? That the standardizing by using mean and standard deviation allow us to do that. So normalizing it is taking the values and putting it towards a normal model. The normal model is a symmetrical and unimodal curve. Standardizing changes the center and the spread of the model, but it doesn't change the overall shape. We can call this normalizing because we take a model that's symmetric and unimodal and make it look like the normal model. We denote it with a capital N, and in parentheses, we write the mean, comma, the standard deviation. That tells you your shape, your center, and your spread. before using the normal model, we do have to confirm that it's appropriate. We can't use a normal model if the data is skewed. Symmetric is what we are looking for. So we have to either look at the data to see if it's symmetric. Sometimes it'll tell you that this data is normally distributed, so we can use the normal model. And if we have the data, we can use a normal probability plot rather than a histogram or dot plot to see if it's symmetric. That's the last one on our graph, and we'll talk about that later. Standardizing allows us to compare two different values. Suppose two competitors are tied after the first 8 events. In the 9th event, the high jump, one clears the bar 1 inch higher than in the 1500 meters, the other one is 5 seconds faster. Who wins? Well, if we knew the mean performance by world-class athletes in each event and the standard deviation, we could compute how far each performance was from the mean in standard deviation units. So how impressive was that compared to all other athletes? How far were you from the mean? And because we want a unitless measurement, we talk about how many standard deviations from the mean it is, and that is called the z-score. The bigger the z-score, whether it's positive or negative, the more impressive or less impressive it actually is. It depends on what you're talking about. If you're talking about a race, a positive z-score is actually negative because in a race you want to be faster, you want to have a lower time. So a more negative z-score is more impressive. But for the high jump, a more positive z-score is more impressive because you want to be higher from the mean. So we're going to do an example in which we consider 3 athletes' performances shown below in a 3-event competition. Note that each one finished first, second, and third at least once in each one. So who should get the gold medal? If each of them got first in one thing, second in one thing, and third in one thing, who gets the gold medal? So we want to know who turned in the most remarkable performance by comparing their performance to the z-score. The z-score calculation, again, is z equals x, my sample, minus the mean divided by the standard deviation. Now this mu is mean and sigma is the standard deviation. Okay, that's our abbreviation in Greek letters. And there's mu and x bar. X bar would be a sample mean. X bar is the mean of all 100-meter dashes recorded for like Olympic or whatever that level would be. So I'm going to calculate the z-scores for competitor A, and then I'm going to have you pause the video and calculate the z-scores for competitor B and C, and then we'll come back together and calculate and talk about who actually won. So for competitor A, we have the 100-meter dash. His z-score, A for the dash, is his time, 10.1 seconds. And we don't put the units in here. Minus the mean, which is 10 seconds, divided by the standard deviation, which is 1.2 or 0.2 seconds. So we subtract 10.1 minus 10 is 0.1 divided by 0.2, which is 1/2 or 0.5. So he is 1/2 of a standard deviation above the mean time for 100-meter dash. And we could say he is 1/2 of a standard deviation slower because being above the mean in a race is actually being slower than the mean. Now we're talking about standard deviation units now. We know he was 0.1 second faster, but we're trying to compare seconds to feet in a shot put in a long jump, and so we want a standardized value that we can compare them to. And so that's why we're talking about how many standard deviations. We're not talking about the seconds. Because in this one, for the shot put, the z-score for A in the shot put is going to be the 66 feet minus the mean of 60 divided by the standard deviation of 3. Let me color code these like I did before. And that is 6 divided by 3, which is 2. So he is 2 standard deviations above the mean, or further from the mean in the shot put. Okay, this is a positive thing. Well, let's note that this is slower. So a positive for the 100-meter dash is actually slower, which is bad, and the positive for the shot put is faster, or farther, which is good. And then the long jump, we have a little bit of an issue here. My standard deviation is in inches and everything else is in feet. So we need to convert 6 inches to 0.5 feet. Remember, the 1 dash is feet, the 2 dashes is inches, and we'll convert this to 27.25 because 3 inches out of 12 is 1/4, which is 0.25. So you have to make sure that when you're calculating z-score, your units are all the same. So we need to maybe do a little conversion here and there. So for the long jump, his score was 26 minus the mean of 26 divided by the standard deviation of 0.5. And that's 0 over 0.5, which is 0. So his long jump score, or distance, is the same as the mean. So pause the video and take the time to calculate the z-scores for B and C in each of their events. Okay, so I'm going to walk through those just to see if you can check your work. The competitor B, his 100-meter dash was 9.9 seconds, minus 10 over 0.2. That's a negative 0.1 over 0.2, which is negative 0.5. That means he was a half a standard deviation below or faster than the mean. So let's look at B's shot put. It was 60 minus 60, right? His score was a 60. The mean was a 60 over 3. That's 0 over 3, which is 0. So the shot put is the same as the mean. And B's long jump, his was 27 feet minus the mean of 26 divided by 0.5. So that's 1 divided by 0.5, which is 2. So his long jump is 2 standard deviations further, that's above the mean. And then for C, his dash was 10.3 seconds minus 10 over 0.2. So that's 0.3 over 0.2, which is 1.5. So he's 1.5 standard deviations slower or below the mean. And the z-score for his shot put. His shot put is 63 feet minus a mean of 60 over a standard deviation of 3. So that's 3 divided by 3, which is 1. So that's 1 standard deviation longer than the mean. 1 standard deviation longer than the mean distance for shot put. And okay, and lastly, the shot put the long jump. He was 27.25 minus a mean of 26 over the standard deviation of 0.5. So that's 1.25 divided by 0.5, which is 2.5. So that's 2.5 standard deviations farther than the mean, and farther is above. Okay, now we have a problem. When we go back and look at our z-scores here, some of them are positive and are good, and some of them are negative and are good. So what we do is for the 100-meter dash, we are going to change them to a negative or we're going to change the sign so that a negative z-score is a bad thing and a positive z-score is a good thing. Because if we add it all together, what happens is we get the better 100-meter dash would actually count against the person if it's negative. So we want to make that a positive thing. So we're going to put A's here as 0.5, negative 0.5. And then this is 2 and 0. And then B's is going to be a positive 0.5 for 100-meter dash because he was faster. So that's a good thing. And we wanted to count for him. And then he had a 0 here and a 2. And then C's was negative 1.5 because he was slower. That's not a good thing. And then 1 and 2.5. And then we can add up their z-scores, and whoever had the highest score now will win the gold. So let's add those up. 2 plus negative 0.5 is 1.5. And so this is our total. And then 0.5 plus 0 plus 2 is 2.5. And then C is negative 1.5 plus 1 is negative 0.5 plus 2 is 2. So here we have first place goes to B, second place goes to C, and third place goes to A.